and the motivation behind the actual challenge itself. What's going on? And I'm going to actually talk about the methodology we use to score the challenge, along with the results themselves. So what we did is we took an approach of taking two different methodologies just to ensure that the scores that we give you guys are actually robust and they're consistent. And Mukesh, where's Mukesh? So Mukesh and Michael helped with the scoring. Please stand up just so people can see you guys and acknowledge your contribution, along with asking them many, many questions after the scoring's done. So if you have any problems, talk to those guys. So I'm going to talk about the Concordance Index, a bootstrap method. I'm going to go over the robustness analysis. So essentially, we give you guys a ranking. We want to make sure that that ranking is robust, that the top team is actually the top team. Go over the actual results, and then a few observations we have. So to make sure we're all on the same page, the Concordance Index is really is what we use to score the challenge. And I'm going to talk through it. I'm going to give you kind of what the interpretation is, and then actually go through the algorithm itself. So what we want to do is we want to build a list of observations. In this case, the observations are the actual gold standard results themselves. And we want to make sure the rank of cell line A is less than the rank of cell line B, or I or J. And then what we want to do is we want to test that against the predictions themselves, and to make sure that the ranks are similar, which would be concordant, or if they're not, then they're non-concordant. Okay? If they're concordant, we add a 1 to the running sum. If not, we add a 0. We go through and make sure we do all these tests, and then we just take the average over all these tests. So that's the Concordance Index, just kind of walking through it. You're going to fall on one end of that range there from I'm sorry? Yes, where is the laser? Okay. You'll fall on the distribution here. 0 being completely anti-concordant, meaning that every prediction you had was completely opposite of the observed. Perfectly concordant, meaning you had the exact same ranking. Or random, meaning you were, half and half. Okay? So the algorithm goes as follows. So we create two loops, and essentially we loop through all of the cell lines, and then we make this test, which is that rank-based test. If we're looking at 4 cell lines, A, B, C, D, N is 4 in this case, first thing we do is say, okay, A is ranked ahead of C in the gold standard data set. What does it look like in the predictions? In this case, it's not concordant. In this case, C and D are ranked 1 and 2, or 2 and 3, and it's concordant in the prediction set. So we go through, we do all these tests, and basically we take the average of that. Now this is great if we actually have a list of absolute rankings where everything's perfect, but as described previously, we do have variance in the data. So if we actually rank the cell lines and look at their GI50 and Sub-challenge 1, we'll find that there is some variance in the actual measurements we have along here. Again, in Sub-challenge 2, the same thing. We have the rank of S over bliss of all 91 combinations, and then we have some variance measured here. And the reason that the little bars are different from here to here is that in Sub-challenge 2, they were able to actually measure variance quite nicely for each of the combinations, whereas we didn't have as many observations for Sub-challenge 1. So we did this pooled standard deviation over Sub-challenge 1. But we have this for 31 drugs. So we try to take this into account in the actual scoring itself. So we came up with a probabilistic way of scoring using a Concordance Index. So essentially the idea is the exact same. We do the same loop, except the tests are slightly different. And again, we're trying to take this distribution of cell line A being ranked here with the distribution, cell line being ranked here. So in other words, there's a probability that cell line B could actually be ranked 1 and 1 could be ranked 2 and so on and so forth. So we want to take that into account. So in addition to the gold standard prediction, we actually have these measures, these scores, and the variance. So if we score this in relation to the distributions, we use the cumulative distribution function to say, okay, A and C is ranked 1 and 2 in the gold standard. It is not concordant in the prediction set. But again, there's a probability that we could be wrong with the actual gold standard, so we try to take that into account. Instead of adding a 0, what we're doing is we're adding a slightly less than half probability that you're going to get a score there. Again, we have C and D, and if you guys participate in the challenge, you'll see that there are some what we call flat profiles, where the actual GI50 is basically the same for a couple of the cell lines. So in this case, essentially these are interchangeable. And we account for that by just saying, we're going to give you a score of 0.5. And in the case here, we have A and B, which is pretty reliably separable from ranked 1 and 4 in this case. It's concordant within the prediction set. So we give you guys not quite a score of 1, but a high score. Okay? So if you participate in Sub-Challenge 2, this was the score that you guys had, and this is how we ranked you. If you participated in Sub-Challenge 1, we had to take one more thing into account. Again, we have 31 drugs, and we want to look at the distribution of the variance within those drugs to actually give you guys a reliability of how well we're able to actually score that drug. So you'll see that there's kind of a flatter profile for drug 1, so we're not as confident in our ranking, in our gold standard ranking. In drug 2, you see that there's a nicer distribution, and the red dots are the test, the black are the training. And what you'll see is that we're able to rank these much more reliably, so we want to weight that higher. Again, this is kind of a poor drug as far as scoring, and then you have a little more variance within drug 4. So if we go through this, what we do is we test the actual test set against the test set. And again, since there's a probability associated with these rankings, what we can do is we can say, okay, drug 1 falls here when we compare it to a completely null distribution of completely random predictions. And then we measure the z-score, and that becomes your weight for drug 1. We do this for drug 2, which is the nice distribution. We have a weight of 4.1. Drug 3, once again, is a poor range, so we have a lower weight. Drug 4, again, so we can go through and give weights to all the individual drugs. And essentially what your score is for Sub-Challenge 1 is the weighted average of those probabilistic Concordance Index values that I described earlier. Okay? So again, we want to make sure that the scores that we're giving each of the teams is actually fairly robust and reliable. So what we did is we independently too. So I did a method. Excuse me. I did a method, and then Michael did a method, and then Mukesh. So we did them independently to make sure that we cross-checked each other. The idea behind the resampled Spearman correlation scoring method is that, again, we're trying to take into account this variance of the cell lines themselves. And instead of scoring your predictions directly against this ranked list, what we do is we create an ensemble of we'll call it the gold standard here. Okay? So there's a couple possibilities of these rankings. We create this null basically ensemble. We compare your predictions to, using a Spearman correlation. You'll get something like this. You'll get a nice distribution of values. Hopefully you're better than random. And then your statistic becomes the difference between your prediction versus a completely null prediction set, which is just, again, it's just completely randomly predicting the rankings. So if you are participating in Sub-Challenge 2, this would be your score for the Spearman, the resampled Spearman correlation. If you participated in Sub-Challenge 1, again, we have to account for the 31 drugs that we're scoring, and we do a weighted average. Okay? So once we actually rank all the teams, we want to make sure that that ranking is robust to certain perturbations in the data. So what we do is we have a way of actually doing this for Sub-Challenge 1. What we do is we have the test set here, and again, there's a little bit of sparsity in the data. But what we do is we mask 10% of the data, which is these little red boxes here, and then we basically rescore your submissions. We do this many, many times, and when you do that many times, you get a nice distribution of actual scores. So we can compare two teams in this case and say, okay, the distribution of this team and this team are relatively similar, so I'm not actually reliably able to call if this team is ranked ahead of the other team. But if you look at, maybe these two teams, you can say, okay, statistically speaking, this team is doing much better than this team. Not worse, just more better or less better, I guess is the description, right? And then for Sub-Challenge 2, instead of masking 10% of the data, since we're only looking at 91 combinations in the first place, what we do is we mask each individual drug iteratively and then go through and rescore. So essentially, we're masking 13 drugs. We have 13 samples that we're able to sample from. And again, you're going to get a distribution of team rankings. Okay? So the actual results for the challenge, again, we had 47 submissions for Sub-Challenge 1. What I'm showing you is the two scoring methods that I described, the weighted average probabilistic Z-index, the resampled Spearman correlation. Here's a null distribution of completely random predictions, And then the little blue dots represent, all of the individual teams. And what we're looking for to see is, are the individual teams actually doing much better than just our null model, which in this case is a random sampling. And, I'd love to talk to you guys more about null models in the case that we're able to actually score these teams, if you guys have ideas. But what you'll see is that the top teams do very well, statistically speaking, in both cases. And these two guys and these two guys are the same teams in the same rankings. So as I talked about the robustness, again, we do the resampling based on masking 10%. And what you'll see is that the top two teams are very robust. If you do a Wilcoxon ranked sum test, what you'll find is that these things are super highly significant. So we're able to actually say Team 1 is actually Team 1. Team 2 in this case is actually Team 2. And from there on out, then we get a little more. Then there's a little more variance in the predictions, and you can say that maybe from team ranked 3 to maybe 10 or so, that you really can't separate those guys. So you guys are. So if you perform third or fourth, you're really in a group of performing second or third. Okay. So for Sub-challenge 2, we had 31 submissions. Again, I'm showing you the Probabilistic Concordance Index, the resampled Spearman correlation, null distribution, individual teams. And there was a bit more of a range of performance, and we can get into why we think that these guys are performing less than random, which we think some people might actually flip their predictions. We tried to solicit people if they wanted to change them, but they didn't. So we had to put them down here. But you still find that you get some very highly statistically significant teams, although Team 1 and Team 2 in this case are not as easily separable. Or I'm sorry, Team 2 and Team 3. So we're able to say Team 1 is Team 1, is actually the rank the best, but there is not as much separation between Team 2 and Team 3. So we're not reliably able to call if the second and third best teams are actually second and third, or more just second best. Okay? And we'll get into the actual teams themselves, but make a few observations on the data itself. So, being part of the DREAM group and the wisdom of crowds, we have to do these types of plots to look to see if we can aggregate individual team performances to see if they'll outperform any of the individual teams themselves. So what I have here plotted is the individual team ranked in according to their performance. The integration, so this little red dot represents the sum of the top 2 teams, top 3 teams, top 4 or 5, so on and so forth. And what you see for Sub-challenge 1 is we don't get much of a boost of performance. You get a little boost up here, but really, you gain most of your top performance with the top, team or 2. And then I did the opposite. I said if you go from the least best team all the way back to the best team, and you integrate, you eventually, get back to the relatively, basically to Team 1. You can make the same observation for Sub-challenge 2, where you actually do see a very nice boost in performance by actually integrating the top 2 performances. So, there's something going on here as opposed to here that, we still don't know what's going on, but we're interested in looking and trying to identify those reasons. So, one of the reasons we do these challenges is to learn something about the data and the methodology themselves. And what we're interested in is so we had teams submit little write-ups associated with their predictions, and then we went through those write-ups and tried to classify the teams based on what types of data they used and also what types of methodologies they used. And this observation has been made a couple times before, but essentially the performance comes down to almost the individual implementation or the little idiosyncratic differences that the teams make, as opposed to any one underlying methodology or approach. So, for example, if you look at all the data sets that were used, a surprising number of teams used almost all the data, but there really was no average better data set. And I think Joe made that observation when he was looking at the data. So it was reconfirmed from your observation. And then no real, the one thing that kind of maybe hurt people's performance was actually trying to impute missing parts of the data themselves. But unfortunately, there's not much we can say about the actual approaches that people took here. Again, it's the individual methodologies, and we hope to learn something about that when the individuals teams talk. Again, for Sub-challenge 2, They had the expression data and copy number variation data. Very few people actually use the copy number variation data. But again, you don't see much difference in the performance, the relative rankings, based on what data people actually used. Real quick, you can then go and look at the individual drugs and see how well people are performing on individual drugs, where you have red is the most concordant, blue is the most anti-concordant. And then we look to see, okay, drug 4 appears to be, this one seems to be able, people can predict this very well. Whereas as these drugs down here, you see a lot of blue, and actually some of these drugs were almost highly anti-concordant, meaning you're almost predicting the opposite of what that actually should be. So there's probably some interesting observations to be made in there, and we hope to explore those further. And for Sub-challenge 2, again, you have the 91 combinations and the relative excess over bliss ranking. And then we can look at individual drugs and see if they have a bias towards being more synergistic or more antagonistic. And you'll see that most of the drugs tend to be a little more, and that's just based on where they fall in the plot here. But you see a couple drugs at the top, rapamycin, kind of makes sense, I guess. And then you see stuff down here like mitacin C, which tends to be more antagonistic. So we're interested in exploring what those relationships are. Okay, so acknowledgement. So there's been a lot of people involved in this process. Sub-challenge 2, Laura, Joe, my advisor, Jim Collins. Sub-challenge 1, Sub-challenge 2, Mukesh, Charles Karn, and then Andrea have been instrumental in getting this done. And I should say, we did for Sub-challenge 2, we did give you guys the data without actually having the gold standard. So Chuck has to be congratulated for actually getting a nice, very nice, reliable gold standard done in that time. Julio, Michael Thomas, and then obviously Gustavo, who's been involved in all these processes. Dan Adina from the NCI. And then you guys, so everybody that participated is considered part of the NCI-DREAM consortium. And we thank you guys tremendously for participating. You always have a little bit of anxiety of, you put a challenge out there. Are people going to like my challenge? Are they going to participate? And we had 52 submissions, which was awesome. So thanks to everybody. And I don't know how you want to do the presentations, but we just go. Oh, so you're going to do the presentation? Okay.